see. Cool. So it's recording.
Great, thank you. So yes, I'm Brent, back again with more Pyomo tips and tricks. Last time I focused mostly on very introductory topics like how do you even set up a model and what are the model components. And I left it mostly at very simple models where there aren't very many technical considerations. Today, I am going to enter the world of graphs, which are a little more tricky than some other types of problems, and then also talk about blocks, which is a specific type of Pyomo object, and implementations, model implementations based on blocks. So just to recall, what is Pyomo? It is a framework, not a solver, for developing optimization models in Python. It is actively developed at Sandia, and it is part of the CoinOR project. This is ripped directly from my previous presentation, as is this slide, which illustrates the dependencies of object construction. So just recall that when we're creating models, we first have to define the index sets, and then from there, we can build the parameters and variables. And then from all of those things, we can build the constraints and the objective function for our model. Today, I'm going to start by talking about graphs, and there will be a couple, ultimately I want to motivate a shortest path implementation, which of course we would never actually solve as an optimization problem. We would almost certainly use Dijkstra's algorithm, which is very efficient. But for the sake of demonstration, I'm going to implement shortest path as an LP. And to get there, I'm going to talk about how we set up index sets for nodes and edges, and the tricky things that occur there. Specifically, how do we handle indexed sets or jagged sets? And then beyond graphs, I'm also going to talk about blocks, provided there's time. And throughout this whole presentation, I know I promised some talk about data integration. So I just kind of intersperse that into all of these examples that I'll be showing. So let's have a look. Here, just a quick note. How do I access the chat? I'm not sure that I can. More chat. So we're going to be working from this Github repository that I just linked in chat. I'll pull it up here real quick on the screen. This is the same as last time, just it's the same repository. I've done a little bit more organization, so these are the things we looked at before. Intermediate, these are the things we'll be looking at today. I have isolated all of the data files that I'm using. So if you want to go and do this on your own, you have access to all of the same data files that I'm using today. And I've isolated them in their own directory here. And the rest of these files are Jupyter notebooks. I also linked in the chat the recording to the previous tutorial, which is being hosted on the UT Informs YouTube channel. So first, nodes and edges. I'm going to create here a random graph, and this is using NetworkX, which is a great Python package for dealing with graphs. And the random graph I'm going to construct has 6 nodes, and the type of graph construction is called Erdos-Renyi. So this P here is talking about a probability of an edge existing between 2 different nodes. And I'm defining this as a directed graph. You know, probably would help if I did a little bit of zoom here. Let's try that. So here's the graph. It's kind of a rough illustration, low resolution here, but you get the idea. So I've created this graph. And what I want to do is from the graph object, extract the edges. So here I'm setting up a dictionary. And then for each edge, I'm creating a random weight for that edge in the graph using a geometric random variable. And now I'm going to take all of this data and compile it in a pandas data frame. Pandas, also another great package for Python, quintessential for data analysts. The pandas, the name comes from panel data, so tabular data, essentially. And so here we have this DF data frame, and I show it. And so right here in the on the left-hand side, we have the indices, the edge indices, and then in the weight column, we have the weight that I randomly generated for that edge. So this is great. Now, why do I want to show this, right? You're making all this random data. Well, it's because in previous examples, we talked about index sets where, you know, maybe you have a set of supply sites and a set of demand sites, and you consider, like for a transportation problem, the types of options you consider, maybe you might transport from every supply site to every demand site, like as an option. And so that would be a complete graph, a complete bipartite graph anyway. But typically in most real world applications, your graphs are not complete, and the edges are a subset of all of the edges in the complete graph. And when I say complete graph, for those not in the know, that is basically just a graph where every node is connected to every other node. So that's typically not the case. Most applications are not on a complete graph. And that can be tricky to deal with in data anyway. Certainly that's trivial to model on paper, but when it comes time to, you know, to actually implement this in code, that can be a little tricky. So what are we looking at here? Really, this data frame that I just constructed is a different kind of representation of, you know, what I might call the weighted adjacency matrix. And if we do a little bit of manipulation here, we can get exactly that. So this is just a different representation of the data, more in the form of a traditional adjacency matrix. And you can see there are several missing values here because there are several edges that do not belong to this graph. The entire main diagonal, because we do not have self loops, and then several of the other off diagonal entries where the edges are absent from the graph. So how do we set this up in a model? Well, one way is like this, where we create the set of nodes, and this is just some fancy stuff. Essentially, I'm just looking at all of the unique values in the index set here. So this is going to create a node set. I'll just pop it up here. So list nodes, right? All I did here is say, okay, so our nodes are labeled 0 through 5. That's all I did. And then I'm creating a model. This is exactly what we saw in the introduction tutorial. I'm creating an index set called nodes, and I'm initializing it with this thing that I just set up here, the node set. Now, when I set up the edges, let's say I want to create the edge set that is the complete Cartesian product of the nodes with itself. So essentially, I want the edges, the edge set, to be every single edge, including the self loops, 0, 0, 0, 1, etc., all the way through 5, 5. It's a good start. It's a good start. Of course, there's a shortcoming here. This is workable because we can say, okay, so we just created an edge for every possible edge that could exist in the graph. And maybe when we go to actually define certain things we need in the model, like the weights, we'll just ignore the edges that we don't actually need. So it's workable, but it's not ideal. And as I'll show in a moment, it's also error prone. As expected, we have 6 nodes. So the Cartesian product of a 6 element set with itself is going to yield a 36 element set. However, we want a subset of that. So let's say instead of here, where we're initializing as the Cartesian product, let's define edges instead Everything else here is the same except for this keyword, which I changed from initialize to within. So essentially what within is saying is, I want my edges to be a subset. It must reside within the Cartesian product of nodes cross nodes, which is fine, but it's incorrect because it's just, you're just specifying the domain and you're still not actually saying what the edge set is. You're not declaring it. You still need to specify initialize here. So of course, the length of the edge set as we just created it is 0. There's nothing there. We just specified a possible domain. So then when we create the edge set, really what we want to do is use both of those keywords. We don't actually need within, but it's best practice, in my opinion, and you're basically getting error checking for free. So what do we have here? Nodes, we're going to define it the same way. For edges, well, we already have this data frame with all the edges as the indices. So let's just use that. The index, we're going to cast it as a set. And now when we create the model, we have nodes, we initialize those, we have edges. We're still saying it must be within the Cartesian product of nodes cross nodes. And we're just going to initialize it with the set of edges we already have from the data frame. And now what should we expect here? Well, something strictly between 0 and 36. And indeed, we have 16. And if we go back up to our graph here, we could probably count and find 16 edges. Some of them aren't showing because it's a directed graph. And so an edge going one way and an edge going the other way, you can't see both. But there are actually 16 edges here. So this is good news. We succeeded in what we wanted to do. Now I'm claiming that this is a more robust attempt than our first attempt, which is also correct functionally. Why? So basically, when we use this within keyword, we're getting error checking for free. And what does that mean? Well, let's deliberately add an edge here. So here we're going to define nodes exactly the same way. For edges, we're saying, yes, let's use the index of the data frame again. And then let's toss in this additional edge that we know does not exist in the Cartesian product, right? Because this is not a node in the node set, 1234. And what happens here is that when we initialize the model edges with this edge set, with this additional edge, Pyomo is going to detect that that is not in the Cartesian product. And indeed, it's warning us of that very thing. It cannot add this value to the edge set. So this is great because sometimes you're going to deal with data that's inconsistent and you're going to assume that everything is hunky-dory when it's actually not. And if you're not careful, Pyomo will burn you. But if you do all the best practice things this way, you're going to detect these data issues well before they're causing you headaches when you're trying to figure out why a constraint doesn't work or why you have more variables than what you expect or something like that. And indeed, without the within keyword, Pyomo will let you put basically anything in here. I think I said it in the introduction tutorial. For Pyomo sets, you can give it anything that's an immutable object. So strings are immutable, integers are immutable, tuples are immutable. So here I'm saying, let's add a tuple of strings. And this shouldn't be here. So even with the tuple of strings, right, we have all the rest of the edges here are like tuple 0, 5, tuple 1, 3, and then we're giving it tuple foo bar, which just doesn't make any sense. But because we did not specify within here, Pyomo allows it. So anyway, this is what you should be doing when you create edge sets. I know it's not super interesting, but it's best practice and it will save you at least once, I'm sure. Now, the benefits, right? So here, I promised to talk a little bit about integrating data. As long as you can get all of your inputs into a format that's either a set or a list, you can use those to parameterize Pyomo sets. And then for pretty much all of the parameters, Pyomo wants you to give it dictionary objects or dictionary-like objects. So a pandas series, which is like the equivalent of a single column, that is what I would call a dict-like object, where there are indices and values, or keys and values. So here, when we initialize, now we're going to use, we're using attempt number 3 up here to parameterize our edge and node sets. And now let's build the cost parameter from the table data. And what we're doing here is saying, well, what is, let's go back. What does df cost look like? It's the adjacency matrix, which is not, it's sparse. And so if we actually use this thing to populate our data, we're going to have an object that's taking up way more memory than we actually need, because it's sparse, but we're having to consider that 0, 0 is not a number and 0, 1 is not a number. And then what we're doing here is stacking it so that it looks more like a series, which again is a dict-like object, a dictionary-like object. And then we can actually cast it as a dictionary-like object by tacking on to dict. And so now that's the actual dictionary. And this is what I'm talking about. So when we use the adjacency matrix, also, sorry, something else to note here. When we stack the data, it's dropping all of the missing values, which is exactly what we want, because we don't want to have those edges in here that are not actually present in our graph. And then we cast it to dictionary. Now the problem, again, using the adjacency matrix is that it's taking up more memory than we need it, right? We only need a very small subset of all of the edges. And then if we use the adjacency matrix, we have to use this extra stack step to actually get the data into a format that we can use. So the point of this is to say that when you're doing data pre-processing for your models, don't try and put it in matrices or anything like that. If you're using Pyomo, just throw it right into a dictionary-like object, a series, and not a data frame. It's a little bit easier to work with that way. So here's a different implementation right here. This was the adjacency matrix, and we were trying to build our cost parameters from that. Now let's just go back to the original data frame that had the weight column, and all we have to do is convert that to a dictionary. So df weight, if we look at the type of that, for a single column, even though it's a df is a data frame, a single column of the data frame is a series. And so that's what we're using here. We're using a series, converting it to a dictionary. And so because it's, it's the same data frame that we used to initialize the edge set, so there's a one-to-one matching and everything's great. Now we have a cost, an edge weight for every single edge that we just defined. Again, this is not very interesting, but these are the kinds of things that you need to consider when you're building a model on a graph. So now let's move into indexed sets before we go to our example. What is an index set? Well, let me build another random graph here. Looks like that. It's a little bigger. I'm going to build a dictionary of where the values are sets to represent the adjacency matrix. So here we're saying node 0 is connected to nodes 1 and 4. I'll also note that I made this an undirected graph, whereas before it was directed. So this is symmetric, the adjacency matrix. 0 is connected to nodes 1 and 4. 1 is connected to nodes 0, 9, and 19. Just go down the list. This is what I'm talking about when I'm saying indexed sets. The set of neighbors is an indexed set. You might say that like the neighbors for node 0 is a set S sub 0, which is equal to 1 and 4. And the reason this is tricky is because these the length of each set is different depending on the index. And Pyomo really does not like that. So actually, when you construct sets like these, Pyomo won't let you do it using sets. You actually have to use a parameter instead. So, here I created this dictionary. I'm just going to convert this into the adjacency matrix to show you exactly how sparse this thing is and why we don't need a matrix. There's a lot of zeros in here. So let's just use the index sets to avoid storing an object with so many zeros in it that we don't need. So like I just said, we can actually implement this in Pyomo, but it's tricky. So we're going to go back here. We created this graph. So now let's create a model where the nodes are the set of nodes in the graph. The edges are the set of edges in the graph. Well, actually here, right, all of this is doing that stuff, just what we saw in the last file. So this is new. We're going to create an adjacent object. So this is basically our indexed set that we're attaching to the model. These sets are indexed in the nodes. So that's the first parameter. Here, we're saying that it can be within Pyomo any. And if we don't do this, Pyomo is going to complain about the default data type, the default domain for a parameter is the reals. So we might, right, if we had a different parameter for the nodes, like, I don't know, just make up some attribute for the nodes and say, node 1 has a value of 5 and node 2 has a value of 10, right? Not node 1 has a value that is a set of numbers, a set of neighbors. So that's why we have within PE any here. It could be that a node doesn't have any neighbors. And so in that case, we want to, just let it be the index set for that node should just be the empty set. And the reason that we don't use this for an empty set is because actually that defaults to an empty dictionary, which is a little bit tricky. So we actually have to say set explicitly here. And then we want to initialize this using this object up here that I constructed. And now we say, right, I had that adjacent object. Now this model.adjacent object that I created from it, if I cast that as a dictionary, it's exactly the same. So we're getting exactly what we want. This is exactly what we want. Now let's make this a little more tangible. Here's a non-graph example. Consider a power grid. The power grid is basically a graph, but let's forget that aspect of it right now. There are a bunch of buses in the graph, or sorry, in the power grid that are effectively nodes in a graph. So think buses are nodes. And at every bus, you might have some number of generators that attach to the grid at that bus. And it might be a different number of generators at each bus. So this is another great application of indexed sets. So here's an example where I have buses A through F and generators 1 through 7. And I'm saying at generator A, there are no at bus A, there are no generators. At bus B, you have generator 1. At bus C, you have generators 2 and 3. Keep going down the list. And so again, this is what we're looking at. This is a dictionary representing a bunch of indexed sets. And we can construct, I guess, the equivalent. It's not exactly, right, it's not a graph that we're looking at here, but I guess you can still think of it as an adjacency matrix where certain buses are they are neighboring, so to speak, the generators. So that's what this is showing here. It's an analog, I guess, not quite the same. And now suppose we want to build a model where we consider active power generation as a variable at every generator. And so we have to create a variable for every one of these bus generator pairs. So we set up index sets for the buses and the generators separately. So there's a set of buses, a set of generators, and then we need to know the set of generators at each bus to allow the model to grasp, what that means. To get it to grok these index sets, we have a pair of objects. One is just the full Cartesian product, sorry, a subset of the Cartesian product of the bus and generator sets. So here we are back to the within keyword, setting up a Cartesian product. And then G of B, this is the index set that we actually instantiate in Pyomo as a parameter and not a set. So here, creating a new model, the buses, we're just setting to be B, which we defined up here. The set of buses is A through F. The set of generators is 1 through 7. B cross G is within, of course, B cross G. We initialize it using the G of B. So basically the adjacency dictionary that I set up. And then we also set up G of B by just passing it G of B. So we attach that directly to the model. It's no different. So I guess this is a little confusing. So you might be wondering, well, that seems redundant. And you're in fact correct. So what does B cross G look like? It's just a bunch of tuples. So this is truly a set of tuples representing all the bus generator pairs. And if we look at this, it's just a different representation of the data. They're essentially capturing the same thing, but doing it in two different ways. So why do we need this? Do we actually need both? Well, no. Really, we only need the former, but it makes creating certain kinds of expressions a little tricky. So the reason we need the former is because to set up variables corresponding to bus generator pairs, we need the set of bus generator pairs. And we can't do that with an index set. So here we're creating variables P, standing for active power. And now if we want to build an expression of all power generated at every bus generator pair, we can do that two ways. We can do it by just summing P indexed in the bus and generator for all bus generator pairs in B cross G, which gives us this expression. Similarly, we could use it, just say for every B, for every bus in the model, let's look at the generators in the index set for that bus. So this is a single for loop in the first way, and this is a double for loop. It's accounting for all of the objects exactly once, regardless of which one of these methods you use. It's just a different way to construct the expression. And I don't know, I guess, is one of these preferable to the other? Not really. Their performance is the same. So really it comes down to your preference, how you prefer to interpret what's going on in the model. But how about power generated at only bus A? So this is all of the power generated at all generators. What about just the power generated at bus A? Well, actually, that's not going to work because I guess our random construction put no generators at bus A. So let's try C. Well, one way is just to say, let's look at all of the bus generator pairs in B cross G, but only the ones where the bus is bus C. And indeed, that's just going to give us the sum of two different variables. Or we could say, let's look at all of the variables. Let's fix the bus to be C, and then let's only consider the variables or the indices G that exist in the index set G sub B, where B is equal to C. So this is exactly the same thing, right? It's accounting for all of the variables that we wish to grasp in the expression once. So again, there's really no performance difference in using one of these. I think the latter is just ever so slightly better. But they're capturing the same thing, just two different ways to do it. One using a subset of the Cartesian product, and the other way using index sets. So now let's look at the shortest path example. Actually, let me stop here because I've been kind of long-winded, and these are not exactly interesting subjects when you don't have an application. So does anyone have questions about creating node sets, edge sets from data, or setting up index sets in Pyomo?
Question on when you do the edges and you actually use the proper subset of the edges that actually exist.
Mm-hmm.
Do you save just on memory, or do you also save on performance when you have a wheel size problem?
Right, both actually. I guess it's a very efficient way to store the data. You could, I suppose, use some other constructs. Like I know NumPy has a sparse matrix support, so you could store it in something like that. Yeah, so I guess it's a little bit of both. You're saving on both memory and time later when you actually need to construct your model from data. Using index sets or using adjacency dictionaries will grant you a little bit of speed up there. I know a lot of people complain that building models in Pyomo is slow, and generally that's true. A big part of the reason that it's slow is because when you actually go and feed the Pyomo model to a solver, it usually has to make a conversion. So a lot of that slowness is just in Pyomo converting the model to a file that the specific solver is able to comprehend. So that's file IO stuff that you're not even doing in your code. It just happens by default. But a lot of times if someone says, oh yeah, it's so slow to build models in Pyomo, and then you go and look at their code and they're doing weird things like triple for loops that aren't necessary and things like that. Right, this is definitely much, much better than a triple for loop or even a double for loop over a sparse matrix.
Okay.
So let's put these ideas into action. I'm using network X again here, but not to create random graphs. I'm actually considering a predefined graph whose data is specified in the notebook here. I'm not loading it from file just yet. This is hard coded. And I don't expect you to immediately grasp what this graph looks like. So I'm going to use network X to draw it. So this is the graph we're considering. And let me just zoom out for a second. It has 10 nodes enumerated 0 through 9, and it is a directed graph, and the edge weights are illustrated on the middle of each edge. So for shortest path, I'm going to consider the start node. I'm going to consider an instance where the start node is 0 and the terminal node is 9. So 0 is down here at the middle of the bottom, 9 is up here at the middle of the top. What's the shortest path to get there? I'm sure you could probably just do this by inspection for a 10 node example, but that's exactly why I want to use it, because the solution should, when we draw the solution later, you should say, oh yeah, his model actually did what I thought it should do. So here we defined nodes as a set, edges as a set, and distance as a dictionary, whose keys are the edges and whose values are the weight or the distance of each edge. So again, this is back to the whole, how do you pre-process your data? Put it into set and dictionary format, and you can't go wrong. Now we need to create a little bit of auxiliary data here. So we're going to create indexed sets at every node for the set of neighboring nodes whose edges are coming into the node, and then another set whose the nodes are for neighbors where the nodes are outgoing. So VM, M is for minus. These are neighboring nodes on incoming edges. VP for plus. These are neighboring nodes for outgoing edges. So I'm just looping over the edges here and creating these, you know, in the way that you probably would all do. And again, we haven't even set up the model yet. I'm just doing a little bit more pre-processing here. So let's formulate the shortest path. Actually, I called it, originally I majored in MIP, but it's actually an LP. So we have a graph. Let S and T be the start and terminal nodes. Let D indexed in I and J denote the distance from node I to J. And then X is a 0, 1 variable, also indexed in I and J, and it just indicates that edge IJ is part of the shortest path, a shortest path, in case there's more than one. And then this is just the notation that I was specifying before, where we have V minus and V plus are index sets for neighbors on incoming and outgoing edges. So in the LP implementation, we're going to impose that one unit of flow enter at the start node and leave at the terminal node, and that at every other node, you just have flow balance. Flow in equals flow out. Whether it's 1 or 0, it doesn't matter. It just has to balance. Then we find the distance weighted sum over the Xij variables, and we use that as our objective function. So that's exactly what we're showing here. For X, the sum of the Xij's where I is fixed to S, that has to equal 1 when those are the outgoing edges. So we're saying over all the outgoing edges at the start node, at least one of them has to be in the shortest path. And then for the second one, we're saying for all of the edges that enter the terminal node, at least one of those has to be carrying the unit of flow. And then this third constraint here is just saying for every node that's not the start and terminal node, impose flow balance. And here again, I'm saying that Xij is, each of them has to be 0 or 1, but we can actually relax that because the constraint matrix is totally unimodular. And if you haven't taken integer programming, I guess let me just say that the LP optimal solution is equal to the IP optimal solution, and that is the simplest way to explain it. Which is nice because that's an easier problem to solve. So let's create the model object. We're defining the sets. So we have the edge set, again, is a subset of the Cartesian product of nodes cross nodes, which we specify here within. I think I copy pasted this about 40 times already. We're going to define the parameters. So again, remember the VM and the VP or V minus and V plus, these are index sets, but we're instantiating them in Pyomo as parameters. In this way, they're indexed in the nodes, and we already set up, you know, pre-process the data to be in dictionary format. So this is a very straightforward process. We're going to define constants here, the model S and T for the start and terminal node. And then the distances are just initialized from the dictionary of distances. To find the variables, there's a variable for each edge. We're going to make it real valued and bound it between 0 and 1, the linear programming relaxation. And then the objective is just the weighted sum of the Xij variables, and the weights are the distances of the edges. Yeah, I don't know why I left that code block there. So for the constraints, I hit on this last time. When you create the different objects in Pyomo, you can usually do it in a more explicit fashion using lists and expressions. The functional programming approach to object creation in Pyomo uses functions which you pass to the keyword argument rule. So this is just explaining, how are rules analogous to expressions, and how is the functional programming paradigm analogous to the imperative programming paradigm. I'm going to skip this for now, but it's in the file in case you want to understand more thoroughly. So basically, I just have a rule that's generating the constraints, and then down here I'm saying let's have a set of constraints called con for constraint flow balance. There's one constraint for every node, and we're going to build those constraints using this function that's defined here. So there's a special case where the node is the start node, the special case where the node is the terminal node, and then if you're any other node except those two, you have flow balance. That's all this function is doing. And now we create our solver from Pyomo opt. So I imported Pyomo opt as PO, creating a solver factory. I'm going to use CBC to solve this because my Gurobi license is expired. And I'm going to T the output so we can see what's going on. This is just, so when I T the output, what I mean to say is I'm T'ing the log that CBC produces when it reads the file and then executes the optimization. So it's telling us it's solved to optimality. The shortest path is 15. The sum of the weights is 15. And if we use the dot value suffix on the variables, then we can figure out what the shortest path is, and it is 0 to 5, 8, 9. So the start node is 0, the end node is 9, and then it visits the nodes in this order along the way of the shortest path. And we can visualize that solution. Maybe you already have this up and you figured it out, you used your highlighter or whatever while I was talking. This is what it should look like. Starting at 0, going to 2, accumulate a cost of 8, accumulate the cumulative cost then becomes 10 when you move to 5, 13 when you move to 8, and 15 when you move to 9. So indeed, right, I trust that this is the shortest path. I'm pretty sure I implemented the model correctly. And this is a great example of how you build a model using an edge set that's defined using the within keyword argument, and it also incorporates indexed sets. So I am running very short on time. There's another example here where I'm doing basically exactly the same thing, except the data is all imported from files. And those files are text and CSV formatted. And I'm using standard Python things to process the text file, and I'm using pandas to process the CSV files. So if you want to look at that, it's exactly the same thing I just showed, just import the data from file instead of hard coding it in the notebook as I did here. So I want to get to blocks because these are very interesting. Essentially, a block is kind of like a submodel in the overarching model. Blocks are Pyomo constructs. Blocks can contain index sets, parameters, variables, constraints. You can attach expressions to the blocks. So I'm going to give an example here of capacitated facility location problem. I'm going to first show it without using blocks, just the way we would have done it if we've done everything as we have so far, and then turn around and say, well, this is what it looks like if you use blocks this way. Blocks indexed in the supply sites, for example. So again, all the data I'm using for this problem, it is included here inside the intermediate directory, it's these 3 files at the top in data. So first, let's set up the solver. We'll use this to solve all the different versions of the problem. What is capacitated facility location? Basically, you have some candidate supply sites and a fixed set of demand sites, and you want to know which supply sites you should turn on and use to transport product to the demand sites. There's a fixed cost associated with turning on a supply site and a variable cost associated with transporting product from a supply site to a demand site. So I'm going to index the supply sites in I and the demand sites in J. S sub I is the supply capacity, D sub J is demand required, F sub I is the fixed cost, and C sub ij is the variable cost of transportation. Xij is the absolute quantity of product we want to ship from I to J. And then Y sub I is just the 0-1 decision to turn on a supply facility. The model is minimize fixed costs and variable costs of transportation, subject to demand must be satisfied and supply capacity cannot be exceeded. And that's it. So we have some variables that are real valued, those are X, and additional variables that are discrete binary valued, 0, 1. So the implementation without blocks. Here's this, oh no. Yep, didn't run this code block. So this is what the data looks like. I basically have some key value pairs in this file. Right, so like demand sites here is a list, which is not quite a set, but you can cast it as a set and it does the same thing. This is just a nuance of YAML. Anyway, I'm importing a YAML file. So we have a set of demand sites, a set of supply sites, and then everything else here you'll see is a dictionary. And so when we set up the parameters, we already have everything we need in key value dictionary format. You know, I've been harping on this the whole time. So we're all set here. We have sets and dictionaries. Everything looks good. So we're creating the model, set up, you know, create I from the supply side set, J from the demand side set, all our parameters, our variables. Again, we have the demand satisfaction constraints and the supply capacity constraints and the min cost objective, where we have fixed and variable costs. So there's nothing fancy here. I'm not using blocks. I'm just using index sets, parameters, variables, constraints, and objectives, as we have been doing this whole time, attaching them all to one single model object. I can solve this, display the solution or display the model after it's been solved, get the values from the optimal solution and optimal solution. Again, I don't know if it's unique or not, but whatever. So there are certain components of this model that you could aggregate, like in a object-oriented programming sort of way. You could say, well, let's just treat the entire demand side as an object. And in so doing, you say, well, what are the, you know, if you do that, if you make the demand side an object, what attributes does it have? Well, the demand side has a demand value. It has a list of transportation costs from all of the supply sites. And what else does it have? Right. So then you also have to make a decision about how much product to transport to the demand site from each of the supply sites. So there are all these things that you could attach to a demand side object in this way. And this is a reason you might want to use a block, is just to kind of like encapsulate all of that modeling for a demand site in a single object. And then you don't have to, the beauty then is that you don't have to worry about indexing in the demand sites within the scope of that object. So let's do that here. Here's a different data file. It has the same information, but I've organized it differently. So I think the only thing here that's the same is the set of supply sites and the set of demand sites. Everything else here is hierarchical, at least everything that pertains to demand. So I have this entire object here of demand data, which is hierarchical. It's indexed in the demand sites A through E, and we'll see that A has a demand and a set of variable costs from the supply sites. B has the same, C, D, and E. Before we just had, key value pairs for all of these things, but now we're presenting the data in a hierarchical format. Fixed costs, those pertain to the supply sites. And since we're not using blocks yet to represent the supply sites, these are not organized in a hierarchical fashion, nor are the actual supply capacity values. So let's actually look at this. Did I import it? Yes. Again, we're going to create the model. We always have to create the model first. We're going to set up sets I and j just like we did before, and attach those directly to the model. These parameters, the supply capacities and the fixed costs, they pertain to the supply sites. They are not indexed in J, the set of demand sites. So we're going to attach these directly to the model as well. And then similarly, the Y variables, the 0, 1 decision variables for supply sites, again, also not indexed in J, so we'll attach those directly to the model. Now let's consider everything that is indexed in J. And we're going to create this rule here, a function, for constructing the blocks. So let's say all of the block data, everything, all the parameters and information we need to create a demand side block is contained in the J index of data, demand data. So the rule is creating the blocks one at a time, one for each J, for each demand site. We're going to borrow the set of supply sites from the root model object. So this is just saying whatever the block is, the model is the model to which it belongs. So that's this thing up here. And we attached the set of supply sites to the model. So we're just saying, let's copy that or use a copy of it here so we don't have to actually create the object, for however many different demand sites there are. And then for D, which is our shorthand for the demand, we're just initializing using the block data demand data. And you'll notice that now, well, this is not very interesting. This is a constant. So the demand site just has a demand that it's not indexed, it's just a fixed value. C, however, recall that the variable costs, they were indexed. And up here, we had to index them both in I and J. But now we're taking J and we're using that to index the blocks. So within a single block representing the demand site, we only need to index C, the transportation costs, in I. And then if we ever want to get the transportation costs associated with the specific demand site, we just reference the block and say, well, what's the the IF transportation cost in the JF block, in the JF demand site. So it's just a little bit different way of accessing the data. But again, this is all about encapsulation here. Again, X, previously we indexed in I and J. Here, indexing only in I, because it already belongs to the JF block. And we're creating a single constraint here. So the demand of the JF demand site must be satisfied. So we're just adding a single constraint here in each block. And then we're creating an expression for the variable cost specific to that demand site. Recall that the fixed costs all pertain to the supply sites. So those don't have to get encapsulated here. And then we just create the blocks in the same way we would create a constraint, using PE block here instead of PE constraint, the index set of the block, and then the rule we're using to construct it, which we just defined above. Now we move to the constraints again. Just like we had parameters and variables not indexed in J, we also have the supply capacity constraints, which are not indexed in the demand sites. So we're going to attach these again directly to the model, and we'll also attach the objective directly to the model. However, notice that when we construct the objective, we're using this variable cost expression that belongs to each of the blocks. So this first sum is the linear combination of y's for the fixed costs. And then the second sum is the linear combination of the xij's, but we're doing it on a block by block basis using the expression we set up. And so we can solve the model this way. And up here, what did we see? The objective value is 5,610 when we solved it the first time. Here, the information is presented a little differently. Now we can see the set of blocks that we created. But if we look at the objective value, we see that it's the same. And I'm pretty sure that the solution is unique. So we can investigate the variables that belong to each block and inspect and see that they assume the same values as before. So I see that I'm at 4, and I know there are probably some of you that want to go to analytics in action. So I'll just say I did a similar exercise where instead of creating blocks that are indexed in the demand sites, you could also index them in the supply sites, which is just a little bit different way to encapsulate the data. I also have a different file, data file, that's hierarchical for this purpose in the, hierarchical in the supply sites. And indeed, we can solve this and see that the objective value is again the same. So this is just 3 different ways to solve capacitated facility location. One that doesn't use blocks, one where the blocks are indexed in the demand sites, and another where they're indexed in the supply sites. And yeah, it was a little short. I ran a little long rather, so I am at the end of what I wish to present. Let's hear the questions.
Yeah, thanks so much, Brent. I was wondering, so going back to like your first examples where you use the within notation when you're defining sets, I was wondering, like, would another application of this be like, you have some subset of your, like, if you have some customer nodes within your set of all nodes, that would be another place where you might want to use this notation.
Right. Yeah, anywhere. Yeah, there are very many applications. I really wanted to hit on graphs today because I neglected it in the introduction. So I just thought of ways where I could use these things specifically for graphs. But you're right, the applications are far more varied than just graphs.
Yeah, it's definitely something that I'll be adding to my code, because I think the error checking utility is definitely something that I could use.
There's also, I want to also mention, there's no reason that you have to limit these concepts to just Cartesian products of 2 different sets. Maybe you have a Cartesian product of 3 sets where the data you have in that, right, you have a very sparse subset within that Cartesian product that you want to consider. You could do exactly the same thing. There's no reason it only has to be for just Cartesian products of 2 sets. I think people are checking out for the seminar, and
yeah, I think we're losing people.
I think I want to be one of those people. So
yeah, sounds great. This was really fantastic. Thanks so much, Brent.
My pleasure. Thank you all.
Yeah. All right. See y'all at the seminar.